This is a short video reviewing some shortcuts for evaluating definite integrals. These shortcuts can be particularly helpful in multivariable calculus. Now, by an integral shortcut, what I mean is evaluating a definite integral exactly without explicitly using the fundamental theorem of calculus, or perhaps a simplification of the use of the fundamental theorem. To get started, let's review what even and odd functions are. Imagine that you have the graph of y equals f of x for some function f. If you reflect that graph in the y-axis, then you obtain the graph of y equals f of minus x. The graph of y equals f of x is shown in gray. The graph of y equals f of minus x is shown in blue. And you can see visually that the blue graph is a reflection in the y-axis of the gray graph. Similarly, if you reflect the graph in the x-axis, then you obtain the graph of y equals minus f of x. In this figure, we again see the original graph in gray and the reflected graph in blue. The general rule is that negating x reflects the graph in the y-axis, or in the x direction, and negating y reflects the graph in the x-axis, or in the y direction. Notice on the right, we write the equation as minus y equals f of x, whereas we usually write that as y equals minus f of x. But this way makes it more clear what the general rule is. Of course, you can also reflect in both axes. Now, reflecting in both axes is equivalent to a 180-degree rotation about the origin. Let's see that visually. So again, a double reflection is equivalent to a 180-degree rotation about the origin. An even function is one whose graph is unchanged upon reflection in the y-axis. Mathematically, that implies that f of minus x is equal to f of x. An odd function is one whose graph is the same when you reflect in either the y or the x-axes. Mathematically, it means that f of minus x is equal to minus f of x. Now, students are often taught that odd functions are the same when rotated around the origin. That is, of course, equivalent, but it makes it harder to see where the equation f of minus x equals minus f of x comes from. Let's look at some examples. X to an even power is even, and x to an odd power is odd. For familiar trig functions, the cosine is even and the sine is odd. The secant is 1 over cosine, so it's the ratio of two even functions, so it's also even. Tangent, on the other hand, is sine over cosine, and since the sine is odd and the cosine is even, the ratio is odd. A sum of even functions is even, and a sum of odd functions is odd. Something like the square root of x squared plus 1 is even, since the argument of the square root is even. And x times the square root of x squared plus 1 is odd, since x is odd and the square root of x squared plus 1 is even, so their product is odd. Now let's look at some integral shortcuts. If you want to evaluate the integral of an even function on an interval that is symmetric around 0, then you can just evaluate the right half of the integral and double it. This is evident from the graph. The red area to the left and the red area to the right of the y-axis are the same. This does not avoid using the fundamental theorem of calculus, but having 0 as the lower limit in the integral often makes it easier to evaluate. If you want to evaluate the integral of an odd function on an interval that is symmetric around 0, then the value of the integral is 0. This is a tremendous shortcut, and you can see that it's true from the figure. The red area to the right of the y-axis is positive, and the red area to the left of the y-axis is the same size, but it's negative, so the two signed areas cancel out. Another shortcut is for the integral of a constant function. In this case, you just get the constant times the width of the interval. You don't need the fundamental theorem of calculus to compute the area of a rectangle. Now, if you have the integral of a sine or a cosine over one full period, then the integral is 0. You can see that in both graphs. The positive and negative areas exactly cancel each other out. Also, if you have the integral of a sinusoid over an integer multiple of whole periods, then the integral is also 0. Now let's look at some examples of these shortcuts in action. First, let's compute the area inside the cardioid given by the polar equation r equals 1 minus cosine theta. We can evaluate this entirely with our shortcuts and no use of the fundamental theorem of calculus. First, we set up the integral, which is 1/2 times the integral of 1 minus the cosine of theta quantity squared over the interval from 0 to 2 pi. We then expand or FOIL 1 minus cosine theta quantity squared, and then use a double angle formula to replace cosine squared of theta. The resulting integral has two constant terms and two cosine terms. Both cosine terms integrate to 0, leaving us with 1/2 the integral of 3/2. So the answer is 1/2 times 3/2 times the width of the interval, which is 2 pi. So we ultimately get 3/2 pi as our answer without any explicit use of the fundamental theorem of calculus. Here's another example. Let's find the area that's inside the limacon given by r equals 1 minus 2 sine theta and the circle r equals 2. The limacon is shown in blue and the circle is in gray. The region we're considering is shown in red in the figure. The area to the left of the y-axis is the same as the area to the right, so let's just compute the area to the right and double it. Now the gray region is just a sector of a disk, so we don't need calculus to compute its area. It's just 1/2 times the radius of the circle squared times the angle, which is pi over 3. For the red region, we integrate 1/2 times 1 minus 2 sine theta quantity squared from minus pi over 6 to pi over 6. To evaluate the integral, first we expand the power. The 4 sine theta term integrates to 0 because the sine function is odd. Then we use a double angle formula for sine squared of theta, leaving us with the integral of a constant plus a cosine. Since that sum is even, we can double the integral and have the interval as shown. Now we don't need the fundamental theorem of calculus for the constant part of the integral, but we do need it for the cosine of 2 theta. But this is pretty easy, and you can see that the final answer is 7 pi over 3 minus the square root of 3. Hopefully you're already convinced that these shortcuts can significantly simplify some calculations, but it gets even better because similar shortcuts are often possible with double and triple integrals. In fact, a lot of problems in multivariable calculus that look complicated can be simplified considerably by using symmetries. For example, consider the function x sine y over the square region shown. The contour map is for x sine y. Now x sine y is odd in x and odd in y, and since the region is symmetric with respect to both axes, the value of the integral must be 0. There's no need to set up an iterated integral and use the fundamental theorem of calculus here. Finally, this triple integral must also be 0 by symmetry. Looking at the figure, the red parts of the solid indicate where the integrand is positive, and the blue parts show where the integrand is negative. Because of the symmetries in the integrand and in the solid, the blue and red contributions to the integral cancel one another out, giving an overall result of 0. Now it's really important to note that you have to have symmetry in both the integrand and in the shape of the domain. You don't want to misapply a shortcut where you don't have both symmetries.